we need to talk about rates of change today. So in the book, we're going to be on page 113, but go ahead and turn there, but we're not quite ready to talk about what's in the book yet. If you look at the screen and you see the graph of f of x, and you see how it's increasing, it's okay that it's squiggly. Since it's increasing, that exhibits a positive rate of change. So whatever it is it's measuring is changing in the positive direction. So it's got a positive rate of change. Now let's pick out a point right here. Let's do that point. Oops. Come on. That point right there. There's a positive slope there. If I drew a tangent line in, it would have a positive slope. So the derivative would be positive. Derivative is rate of change. It has a positive rate of change here. If I pick out a point over here, the slope of that tangent line is also positive, but it's a much bigger number, isn't it? That slope's much greater. The slope of point A is much greater than the slope of point B. So the rate of change at point A is greater than the rate of change at point B. Whatever it is that's being measured by this graph is changing much more quickly at a much bigger rate at point A than it was at point B. Does that make sense to you? Well, then look at g of x, because whatever's measured here is decreasing. So there's a negative rate of change. And if I pick point C right there, the slope of the tangent, which is the derivative, is negative. And if I pick point D down here, the slope of the tangent is much steeper. The absolute value of that slope is much greater. The rate of change is greater again, isn't it? It's in the negative direction, but it's a bigger rate of change. Okay? You with me? All right. Now what if these are velocities? So that's rate of change in general. Okay? So what if these are velocities? For f of x, our object is going in the positive direction. Maybe forward, maybe up, maybe to the right, whichever way we decide is the positive direction. G of x, the object that's being measured there, is going in the negative direction. Maybe it's going down, maybe it's going to the left, maybe it's going backwards. If the slope here, let me just make up a number. If the slope here was 22, so the derivative equals 22, and the slope here is negative 22, so the derivative is negative 22. Let's say this is a car moving, okay? And that car, it's a crash test, and that car hits the barrier, the wall, or whatever. When is it going faster? When it's 22 or when it's negative 22? It's the same, isn't it? All right, because velocity has a direction. Positive velocity means whatever you've decided the positive direction is. Up, to the right, forward. Negative velocity goes going in the negative direction, down, left, backwards. But the speed of the object is actually the absolute value of the velocity. Okay? So there's just as much, trauma to the vehicle going positive 22 as the velocity as negative 22 for the velocity. Okay? All this making sense to you? Okay. Now let's look at what the book has to say. On page 113. It says, you have seen how the derivative is used to determine slope. The derivative can also be used to determine the rate of change of one variable with respect to another. Applications involving rates of change occur in a wide variety of fields. A few examples are population growth rates, production rates, water flow rates, velocity, and acceleration. A common use for rate of change is to describe the motion of an object moving in a straight line. In such problems, it is customary to use either a horizontal or a vertical line with a designated origin to represent the line of motion. In other words, you need to have an origin. okay? And you might as well either make it horizontal, the x-axis, or vertical, the y-axis. Where'd I get? On such lines, movement to the right or upward is considered to be in the positive direction, and movement to the left or downward is considered to be in the negative direction. All right, the function s that gives the position relative to the origin of an object as a function of time is called a position function. For some reason, and I'm sure there actually is a reason, s is the general term or general letter we use to name a function when it's describing the position of a moving object. All right? So s is the position function. Now, things move with respect to time. So whenever we have a position function, we almost always want to use t as the variable t for time. Okay? There's no law that says you have to use t to stand for time, but it seems reasonable. So let's use t for time. If over a period of time, delta t means change in t, change in time. The object changes its position by the amount delta s equals s of t plus delta t minus s of t. Okay, I could be losing you here at this point. If we've got a t-axis and a y-axis, t for time, y gives you the position of the moving object at that time. Okay? So we would start at 0, 0, 0 for the position, 0 for the time. All right? Then the object moves. Okay? In this case, the object would be moving in the positive direction. The velocity is positive. So the rate of change is positive. Now, in general, before we knew anything about derivatives, we could find an average rate of change with a secant line, right? We would take the original position, well, actually, we would take the new position, subtract the original position from it, and that's how far the object has moved, right? Wherever it ends minus where it started, that's how far it's moved. Well, that's what that is. That's y2 minus y1. Okay? Remember how we had f of x plus delta x as our y2 and f of x as our y1 with the slope formula? It's the same idea. It gets confusing because now it's different letters. You finally got used to the f of x plus delta x. Now we've changed the letters on you. But it's the same idea. It's the position where the object ends minus the position where it started. y2 minus y1. Okay? Now when I say it ends, that for this measurement, it may keep going and we measure it again. But for this measurement, y2 is where it ends, y1 is where it started. Okay? Now, if we were going to find the slope of that blue line, that secant line, wouldn't we have that as our denominator? And since it's time, maybe instead of x's, I should put t2 minus t1. You following me? And couldn't we call that delta t? All right, so the notation can be an issue here. You can understand what I'm talking about and let the letters confuse you. Let's try to avoid that, okay? You need to understand what I'm talking about, and you need to understand that those letters are expressing the same idea as I am. So that means that our average rate of change, and if this is a moving object, we can call this the average velocity, average rate of change, average velocity, is the change in position, which we can call y2 minus y1 over the change in time, the amount of time it took, which we can call t2 minus t1. You need to put that in your notes. Yeah. So put all of that in your notes right here. And while you're writing, be thinking about it and see if you have any questions for me. T for time. S, for some reason, S stands for position. Kind of like M stands for slope, and I don't know why. S stands for position, and I don't know why. I know there's a reason, I just don't know what the reason is. It could, yeah, it could be. Okay, you with me? Now, quite often, knowing the average rate of change is good enough, right? But sometimes it's not, okay? You're going from here to Paducah, and your average velocity is 50 miles per hour. When you're going 70 on 641 and the cop pulls you over, it does you no good to argue, but my average velocity is only 50 miles per hour. Because your instantaneous velocity was 15 miles per hour over the speed limit. And you're done. And you deserve the ticket. Slow down. Okay? So sometimes the instantaneous velocity is a lot more important than the average velocity. And sometimes the average is more important. If I'm going on a long trip, I kind of want to know how long it's going to take. I want to know the average rate of speed I'm going to be able to go, not at any given moment, right? So sometimes we need one, sometimes we need the other. Well, think about it. Doesn't this look familiar? Because like you just said, all we did was change the letters. If I took the limit of that as delta t approached 0, wouldn't that be the derivative? So to go from the average velocity to the instantaneous velocity, all I have to do is find the limit of that as delta t approaches 0. Okay? So in other words, the derivative gives me the instantaneous velocity. You with me? Yes. So we would be coming up with a formula to find the instantaneous velocity at any given time. All right, so let's read what the book says. It says, suppose that in example 9, you wanted the instantaneous velocity, which we're just going to call velocity. Okay? Quite often I will say instantaneous velocity to remind you that it's the derivative version, not the average velocity. Okay? But you don't have to say the word instantaneous. If you say velocity, it means instantaneous velocity of the object when time equals 1. Just as you can approximate the slope of the tangent line by calculating the slope of the secant line, you can approximate the velocity at t equals 1 by calculating the average velocity over a small interval. So, just like we did before when we kept moving p closer to q, same idea. If I want to know what the instantaneous velocity is right there at that point, I can do it by finding average velocities and then narrowing the interval down, right? And I'll eventually find, oh, every time I make the interval smaller, delta t smaller, the velocity, the average velocity gets closer to 70 miles per hour. Okay? It's okay. In fact, it's kind of funny. So, by taking the limit as delta t approaches 0, you obtain the velocity. Okay? All right, so, let's see, what else do I want to... I'm going to have you write this in a minute, but not yet. Look what they've got here. They've got the average velocity They took the limit of it as delta t approaches 0, which we'd already talked about. That would be the derivative. So you can call that s prime of t. Instead of f prime of x, it's now s prime of t. You can also, since velocity is a very useful function in and of itself, you can also just call it v of t. Okay? So put this in your notes. And if you're following along in the book, we're actually over on page 114 now. If you're ever working on this and all of a sudden you're like, ah, crud, it doesn't make any sense at all to me anymore. It did setting in class, now it doesn't. And now does it make sense again? We're just using different letters. Okay? All right, now, like we'd already talked about, the speed of an object is the absolute value of its velocity. So speed is never negative. It can be 0, I mean, right now the speed of my car is 0, I hope. Okay? But it'll never be negative. The velocity can be negative. I can back it up, but the speed will never be negative. So also in your notes, put this, that velocity gives direction, positive or negative, and speed equals the absolute value of velocity. And while we're on the topic of objects in motion, put this in your notes too. Acceleration is the rate of change of the velocity. That's what acceleration is. We use the term acceleration. We don't always know what it means. It's just a way to measure the rate of change of the velocity. In other words, think of this, okay? You could be driving forward, but slowing down. Your velocity is positive because you're going forward. Your acceleration is negative because the rate of change of the velocity is negative. You could be driving forward and speeding up, so your acceleration would be positive then. See what's going on? So, if the acceleration is the rate of change of the velocity, that means the acceleration, a of t, a, get it, a for acceleration, equals v prime of t, the derivative of the velocity function, and check out this cool notation, equals s double prime of t. Guess what double prime means? The derivative of the derivative. So you start with s. Listen to me now. You start with s. You take its derivative, you get velocity. You take the derivative again, you get the acceleration. You start with s. You take its derivative, and you get the velocity. You take the derivative again, and you get the acceleration. position of position. I'm not sure I follow everything. Let me say it this way. You start here. That's your position function. You can graph it and everything, right? You take the derivative of that, and you will get a formula for the velocity. So the velocity itself is a function. You take the derivative of that new velocity function. No, after 2 comes 3. So the second derivative of the position is the first derivative of the velocity, and that's what we call acceleration. Correct. Is that what you're saying and I'm just not understanding you? Okay. Okay. Thank you, Charlie. All right. Let's see if I cover everything. Okay. In general, and you don't have to memorize this yet, in general, if you've got a free-falling object and you neglect air resistance, can you really ever neglect air resistance? Not really. Okay? That's the position function of a falling object neglecting air resistance. It's 1/2 times the force of gravity. What is the gravitational constant? 9.8. Okay. T squared plus the initial velocity times t plus the initial position. So everybody's writing that down. You don't have to know that yet. But some of you already do, right? Okay. And if you're measuring in meters, that's G. And if you're measuring in feet, that's G. Yeah, we do feet. Calculus is an American thing. We like feet and seconds. See, why? Shouldn't they have changed that too? Because time's harder to deal with than feet is. Because, you know, the old 60 seconds in a minute, 60 minutes in an hour gets confusing sometimes. Why didn't they make it 100 seconds and 100 minutes and 100 hours? And by the way, why don't we use military time? Because that's a lot simpler. Instead of saying 1 p.m., why not just say 13? I mean, it makes more sense. All right. I'll get off my rant. All right. Here's what you got to make sure you know. You've got to know this. You've got to know that velocity gives direction, positive or negative, that speed equals the absolute value of velocity, that acceleration is the rate of change of the velocity, that acceleration is the derivative of velocity, which is, and is the second derivative of position, and you got to know, and we've talked about this 100 times, that the derivative of a function is the slope of the tangent line or the slope of the graph of the function. It's also the rate of change, instantaneous rate of change, not average rate of change. It's also the velocity, instantaneous velocity, not average velocity, of an object whose motion is represented by the function. You've got to know those 3 things. All of them will be asked 20 different ways on the AP test. It's the same thing every time. But that's the point. You got to understand that all 3 of those things are the same thing. Okay? So what do you say we work a few problems? Does that sound fun? Yeah. All right, we're going to start with number 62 on page 116. It says, determine the points, if any, at which the graph of the function has a horizontal tangent line. So we actually could have worked this the other day, all right, but we just didn't have time to get to it. So determine the points, if any, at which the graph of the function has a horizontal tangent line. What's the slope of a horizontal line? 0. So we need to find the derivative, because that's the slope of the tangent line. And what does the derivative need to equal? 0. And that'll tell us where we have a horizontal tangent line. So on 62, we start off with y equals, and I don't really like their notation there. That square root of 3x, the x is not supposed to be under the radical. So I probably would have written it as x square root of 3, but the x is not under the radical. Plus 2 cosine of x, and they give us an interval from 0 to 2 pi. That's good, otherwise we'd get a bunch of different answers. Okay? All right, so let's take the derivative, because the derivative is a formula to find the slope of the tangent line. So we take the derivative. Now, it looks funny, but the reason they wrote it with the square root of 3 in front is so that you would say, like if we have the derivative of 2x, it's 2, right? So the derivative of the square root of 3x is square root of 3. It's the combination rule. Square root of 3x, take its derivative. So you got exponent of 1 times the coefficient, x, subtract 1 from the exponent. Well, that's a 1, so square root of 3. Plus, now use the constant multiple rule. The derivative of 2 cosine of x is 2 times whatever the derivative of the cosine of x equals. And the derivative of the cosine of x is negative sine of x. And then I'll like it a little bit better if I don't have the parentheses. So y prime equals the square root of 3 minus 2 times the sine of x. What do we do with this? Well, instead of using that to find a slope at a given point, we know what the slope has to equal. And we're going to figure out at what point or points does that occur. Since we have a horizontal tangent line, the slope has to equal 0. Since the derivative is a formula for the slope, then the derivative has to equal 0. So we're not doing the same thing we usually do. We're not finding the derivative and then plugging in an x and seeing what the slope equals at that point. It's the opposite. We found the derivative. We know that the slope equals 0, and we're going to solve for x and see where this occurs. Make sense? All right. So square root of 3 minus 2 times the sine of x equals 0. So if I subtract the square root of 3 from both sides, I get negative 2 sine of x equals negative square root of 3. And then I ran out of paper. So you can just keep going down. I had to go over to the side. Then I divide both sides by negative 2. And I get the sine of x to equal the square root of 3 over 2. And then I look at my little trig chart. And I see that on the interval from 0 to 2 pi, that there are two different places where the sine equals the square root of 3 over 2. When the angle is pi over 3, the sine is square root of 3 over 2. And when the angle is 2 pi over 3, the sine equals the square root of 3 over 2. So that means there are two different places from 0 to 2 pi where this graph has a horizontal tangent line. When x equals pi over 3 and when x equals 2 pi over 3. You with me? All right. I wish we were done. Sometimes we will be. It depends on how they word the question. They said determine the points. All we've found so far are the x coordinates. So now we got to go get the y coordinates. So, horizontal tangents at pi over 3 something and 2 pi over 3 something. Plug in where? Plug in for x, but where? On the y prime one? So go back up there, and that way you'll find the y coordinate and the y coordinate, and they're messy. So keep them messy. I don't mind. Actually, I do mind, but keep them messy. All I did was evaluate the cosine of pi over 3 and the cosine of 2 pi over 3, and I left the rest of it there. Because you get into one of those situations of, okay, do I really want to take 10 minutes to simplify that into one little fraction? If it's a test, yes. If it's a homework problem, no. Move on to the next. All right, we good with 62? Any questions? Now, if that didn't have the cosine in there and it had just been a polynomial, that's a fairly easy problem. Fairly. I'm not saying it's a piece of cake. But the hard part was, you had to remember how to work with trig. Yay, trig. All right, we ready to move on? Number 90. Find the average rate of change of the function over the given interval. Compare this average rate of change with the instantaneous rates of change at the end points of the interval. So f of t equals t squared minus 3, and they give us a closed interval from 2 to 2.1. So that's a pretty small interval. With a small interval, I would expect the average rate of change to be fairly close to the instantaneous rate of change. Now, what's close to? I don't know, okay, because that's true. All right, so f of t equals t squared minus 3. According to our notes that we took, the average rate of change, we had it with s's, right? We called it average velocity, and we had s of t plus delta t minus s of t over delta t. But what that really means is y2 minus y1 over x2 minus x1. That's how we want to find the average rate of change. So the ending point, the stopping point, will be the position when x equals 2.1, right? So f of 2.1, that's our y2. Minus, and the beginning then was when t equals 2. So f of 2 is where we started. So the change in position is going to be where we ended minus where we started. So f of the time we ended minus f of the time we started. Does that make sense? Because I never phrased it quite like that before. T is x. Yep. Yeah. All right. The denominator, x squared or x2 minus x1. In this case, it's t. So t2 would be 2.1 minus t1, 2. All right. So you with me this far? All right. So what is f of 2.1? Well, you plug 2.1 in for t. So instead of t squared minus 3, it's 2.1 squared minus 3 minus f of 2. So instead of t squared minus 3, it's 2 squared minus 3. Over 0.1, because 2.1 minus 2 is 0.1. Then you do a little math here. Square the 2.1, you get 4.41. Square the 2, you get 4. Leave the 0.1 in your denominator. There's where I've been trying to get to. I'll stop there for a second. Get caught up to me. That's where I'm at. Okay? Y2, the position at the end of the interval is 1.41. Took me a few steps to figure it out, but I mean, I'm going to have to figure it out, right? I got to figure out the position when the time ends. So Y2, turns out it's 1.41. Minus, and then what was the position when we began measuring? Well, it was f of 2, which turns out to be 1. And then the bottom, the delta t, the change in time. If I'd never written it in here, if I didn't write that in, if I just gave you that, I said, how much time passed? Wouldn't you say 0.1? 0.1 seconds, 0.1 minutes, 0.1 hours, whatever it is? That's what that is. Okay? So it took us a few steps, but all we've done is arrived right here. With me? I know, you just finished doing the math. So 1.41 minus 1 is 0.41, and then 0.41 divided by 0.1 is 4.1. We found the average rate of change. Now, they didn't give us units, but yeah, maybe it's feet per second, miles per hour, whatever, okay? All right, so that's the average velocity, the average rate of change for that object from time t equals 2 to time t equals 2.1. And again, I don't know if it's feet per second or what. They didn't tell us. Assume it's feet per second, if that makes it make more sense to you. Okay? Now, we're supposed to compare this to the instantaneous velocity at each endpoint. How do I find, in general, the instantaneous velocity? Right. And now that we've learned our derivative rules and all, can't I just use whatever my derivative rules are? It's the derivative, right? The derivative is the slope, it's the rate of change, it's the velocity. So find the derivative. Well, if our function f of t is t squared minus 3, according to the power rule, the derivative of t squared is 2t, and the derivative of a constant is 0, so the derivative of negative 3 is 0. So f prime of t simply equals 2t. The derivative is a formula, so where are we supposed to use this formula? At each endpoint. So find the derivative when t equals 2, and find the derivative when t equals 2.1. When the derivative when t equals 2 will be 2 times 2. The derivative when t equals 2.1 will be 2 times 2.1.
So the f of t, like on our notes, would be just s of t.
Correct. Yeah, see, they keep screwing with the letters, don't they? They teach it to us as s of t, and then the first problem I work as an example for you, it's back to f. If that had been s, that would fit our notes, wouldn't it? So get used to that. Then when you take the AP test, it's all G's and H's, because they know that nobody learns it with G's and H's. So they change the letters to make sure you actually understand it instead of or just mimicking what I've done. Well, we work a lot of problems with G's and H's. But if all the books start using G's and H's, they'll switch to something else. You know?
You know that, why don't you?
Well, we do have G's and H's. Be patient. We're early in the school year. All right. Now, hang on just a second. Can we tell anything from looking at the average rate of change and the rate of change at each endpoint, do what? No, I wouldn't say that. When t equals 2, the rate of change is 4. When t equals 2.1, the rate of change is greater. So isn't this thing accelerating? Positive acceleration? All right, Alex, your question?
The very first thing we did with the equal 1 minus f of t.
Uh-huh. Uh-huh. Yep. When we didn't take the limit, it gave us the average rate of change. When we take the limit, it gives us the instantaneous rate of change. I think of it like this. I honestly do. That's the position where you end. That's the position where you begin. That's the time when you end. That's the time when you begin. I haven't run into a situation yet where that didn't serve me well.
Where is the 2t come from? How do you know it's 2t?
Because that's our function. Its derivative is 2t. You talking right here? Yeah. So if 2 days ago I'd given you this problem, f of t equals t squared minus 3, and it said use your new derivative rules to find the derivative. You say, okay, well, f prime of t equals, use the power rule, that's 2t, subtract 1 from the exponent, so t to the 1, and then the derivative of negative 3, the derivative of a constant is 0, so 2t. All right? All right, let's try to squeeze in one more example here if we can. In exercises 97 and 98, the graph of a position function is shown. It represents the distance in miles that a person drives during a 10-minute trip to work. Make a sketch of the corresponding velocity function. All right, so there's where I'm going to sketch my velocity function. For this part of the graph right here, what's the approximate slope of that graph? It's pretty close to 1, right? So, yeah. So, and does it change? Does the rate of change, or is it constant there? It's a line, so it doesn't change. So that means from 0 to 6, the velocity is a steady close to 1. Okay? Now, from 6 to 8, the distance doesn't go up at all, does it? The distance did not increase for those 2 minutes. So what's the velocity for those 2 minutes? It's 0. Now, nope, we're graphing the velocity. Because look what's happened. They start at, because the graph they give us is position. They start at 0, 0, they end at 6, 5, and they had a constant motion there, no curve in. So that means the derivative, like if that was 1, y equals 1x, well then the derivative would be 1. So that's how we got that horizontal line there. All right, and then look what happens from 8 to 10. We're back to we're moving again. Is that slope?
It's a little less.
It's a little bit flatter. It's not. They're not going quite as fast.
Going half
Nah, it's rough, right? Now I have a question for you. What should I put at the ends of those 3 different little segments? Should open circles? Why should they be open? We need some we we can't have them closed everywhere, right? Because then we'd be doing two things. But and, I'm a little bit unsure of what to do. I mean, I'm not setting you up. I really am, because the velocity is what it is until it's not. You know what I mean? Okay. So, close them down here if you want, or close them up there if you want, but don't make them overlapping. Then it's not a function anymore. So I think I'll just leave them open both places and hope that whoever's grading this doesn't notice. All right. Woohoo! You will not get this finished tonight. Get as much of it done as you can.